Topic 3.4, Ideal Gas Law. If you're following along with me as I'm putting these videos out, you probably noticed that I skipped 3.2 and 3.3. Both of those have to do with the structure of solids and liquids and gases. I kind of went over that a little bit during states of matter, and honestly, there's not much really to say there. So I'm going to skip those for now, and I might come back to them later on if we have time. So right now, we're going to jump straight into ideal gas law. The big thing with ideal gas law you need to remember is the ideal gas law formula, PV equals nRT. I'll get into that a little bit whenever we head over to the slides. So the other thing you need to know other than PV equals nRT is that the total pressure of a system is the partial pressure of each gas summed together. The ideal gas law is actually a combination of several other gas laws: Boyle's law, Charles' law, Avogadro's law, and a few others. And this kind of goes through, I'm just kind of summing them up here. This is them kind of summarized together, and you can see how you can kind of add these together, Voltron style, into getting PV equals nRT. Now, what exactly are these things? P is your pressure, V is your volume, N is the number of moles, R is your ideal gas constant, and T is going to be your temperature. Now, if you change one of these variables, the other things are going to change as well, unless they are being held constant. So, for example, volume, if the container that the gas is in is something elastic like a balloon, then the volume is going to be allowed to change. If it's something rigid, that means it's going to be unable to change. You're going to not change the volume of it. The number of moles, if there's no chemical reaction going on and no gas is escaping or being added, the number of moles is going to stay the same. Temperature, you can imagine holding the temperature constant or allowing the temperature to change. And then pressure, same thing. If you allow the pressure to change, or you can keep the pressure constant. And usually in a problem, they'll go through and they'll say, a rigid container at constant pressure and temperature, something along those lines, to let you know which ones are constant and which ones are not. What I want to do is go through and just say, how will these guys all affect each other? How will all of these guys affect each other? What would happen if I increased pressure? If I increased pressure and everything else was the same, what would happen to volume? Well, if I increased pressure and nRT remained the same, what would volume have to do? Well, volume would have to go down. And that should make sense. If you have a balloon and I squeeze it and I'm increasing pressure, what's the balloon going to do? The balloon is going to get smaller. So that kind of makes sense. So you can do that with all of these guys, not just with volume. If I increase pressure, what's going to happen to the temperature? Well, if I increase pressure, volume stays the same, number of moles remain the same, and R remains the same. What's going to happen to the temperature? The temperature is also going to increase. So we can think about that when we get into kinetic molecular theory. We're going to talk about why that is. And to give you a preview, it's because when you increase the pressure, you're increasing the number of collisions that are happening, and that's going to increase the average kinetics that are going on inside of the container. You can do the same thing with all of these guys. If you increase volume, what happens to the temperature? Well, that means it's going to increase as well. If I increase volume, what's going to happen to the pressure? Pressure is going to go down. You can do that with all of these guys. Now, when it comes to number of moles, this is going to be a little bit going into equilibrium. If we have an equilibrium, and let's say I have 2A on this side and I have 1B on this side. If I increase pressure, the number of moles is going to try to go down, which means that it's going to shift this equilibrium over to the right hand side. So that's a little peek into equilibrium stuff. Some other things that you need to remember. A lot of times you're going to hear this phrase, STP. This is going to be standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, and 1 atmosphere. That is the standard temperature and pressure. Now, usually you're going to be working in Kelvin. If you have a problem and they're giving you Celsius, it's probably going to be the best idea to go ahead and convert that over to Kelvin. It's easy enough to do. You're just going to add 263.15 if you want to get really technical. Now remember, there are a lot of different ways of describing pressure. Typically, we're going to use atmospheres, but you can also use torr. You can use PSI. You can use there's about 300 different ways of describing it. That's hyperbole. It's not actually 300. But so there's a lot of different ways of talking about pressure. There's lots of different ways of talking about volume as well. There's liters, there's meters cubed, feet cubed, centimeters cubed. There's a lot of different ways of talking about volume. And number of moles, that's always going to be the same. Temperature, typically you're going to, again, like I said, we're going to be talking about temperature in terms of Kelvin, but you could imagine a world where you might want to use Celsius instead. And that means that the units for R and the value for R is going to change based on your units. So that's one thing you want to look at. In your problem, how are they going through and telling you what is the pressure, volume, moles, and temperature, and then pick which gas constant you need to use. I'm going to let you guys know the most common one that is out there is probably going to be this one, and 0.08205657. And that's just because atmospheres, liters are such a common way of going about it. Another one that's used fairly often is torr. Both of these are going to be on the constants and equation sheet. I'm going to say this, with isolation going on right now, if you don't have a constants and equation sheet, you can find one online. If you just type in AP Chem constants and equation sheet, you will you can find one, print it out, or at the very least have a PDF of it so you can have it available for your exam. And I know this is, if you're watching this in the future, remember, the isolation of 2020. I don't think the world's going to forget that anytime soon. So things were a little bit different at this time. That is basically how you're going to go through and work with the ideal gas law. It's going to be basic algebra. If you're given everything except one thing and they're asking for pressure, for example, you can just use some algebra to rearrange this to get what you want. So if you're looking for pressure, it would be pressure equals nRT over volume. So this would be what you do. Then at that point, you would just plug and chug. Sometimes they'll say the pressure is changing. What would that be? In a different video, I'm going to go through and just work through a bunch of problems to kind of show you how I go about working these problems. It can be very helpful to see someone work through these problems and kind of get a rote procedure. But I feel like the best way for students to go through that is to develop their own procedure. That way you have some ownership of it. Or if you see me doing it and you like the way I do it that way. That's the ideal gas law. Let me talk a little bit about, so the other thing that I want to talk about is Dalton's Law of Partial Pressures. Dalton's Law of Partial Pressures says that the if you have a mixture of gases, in this case, if we're talking about just like our typical air that we breathe in, we're going to have some sort of pressure, and this total pressure is going to be made up of the pressure that's given off by the CO2, the H2O, argon, nitrogen, and all the other gases that are that make up this mixture of gases. So just remember that the pressure total, is going to be equal to all of these pressures summed together. So you can think of it as the pressure of your first thing plus the pressure of your second thing plus the pressure of your third thing, and so on and so forth and so on. We'll get into the why of this when we talk about KMT, kinetic molecular theory. But for right now, just remember the total pressure is all of the partial pressures summed together. If you don't know the partial pressure, or if you know the total pressure and you know the pressure of A and B, it would be pretty easy for you to figure out what the pressure for C is. If I say 100 equals 13 plus 56 and something else, what is that something else? At that point, it's just kind of basic algebra. All right, so that's going to be the video. Like I said, there's going to be, I'm going to make another video going through some of these problems, but I wanted to just talk about it beforehand before doing that. All right, I will see you guys next time.